Hi, everybody. I think we're going to go ahead and get started. I just wanted to welcome you to the March webinar here at CARS with Changliu Liu, who was a CARS fellow last year and is going to be sharing her research with us today. Before we get started, I have a couple of quick announcements. Pardon me, let me just advance the slide here. A couple of quick announcements. One is that tomorrow at Stanford at 9:30, there's going to be a Meet the Makers event at the Product Realization Lab. So students are going to be presenting work that they have done in the making space, either fabricating mechanical devices, electrical devices. In some cases, it's consumer goods and educational projects. So please feel free to come by that. It's building 550, which is the D school here at Stanford, and let us know if you have any questions. The second announcement was that the Stanford Solar Car project is getting underway. The molds that you see on the top left side are the molds for the new car. The car is in fact much longer and much narrower than the previous car. The students are going to be beginning the carbon fiber layup process here at Vail in that wooden box that you see that's behind Vail right now. And the new car should be well underway in terms of fabrication just in the next few weeks. And we'll have a big reveal event sometime late this spring or early this summer that we'll invite the CARS affiliates to. Also wanted to make the announcement that Adele and I are planning some trips for later this year. I'd like to try to visit CARS affiliates as frequently as we can. So in April, I will actually be in Korea. So if any of you have colleagues in Korea that you think might like to talk to us, please let me know. I'll be there April 2nd and 3rd. We'll have some free time to potentially meet with affiliates. Late this summer, Brian Casey and I, the CARS legal fellow, and I will be visiting the Northeast United States, probably Boston, New York, and Washington, D.C. to talk about some of the legal aspects of automated driving, some of the work that Brian Casey has published recently. And in mid-September, we'll be traveling to Germany. So please let us know if you're interested in meeting with us any of those locations and dates, or if you'd like us to stop by and visit you at a different location. Lastly, I wanted to thank the folks. I see Stefano, I see you online specifically, so I'll thank you specifically for coming out and judging Principles of Robotic Autonomy with us on the 15th. It was an awesome event. Thank you so much for your support. Thank you for your involvement with that class. So without further ado, I think I'd like to let Changliu go ahead and take this away. Changliu is a former CARS fellow who's here for the past year and was recently offered a position as assistant professor at the Robotics Institute at Carnegie Mellon University, where she's now begun her work. And this work that she's going to be presenting today is specifically focused on verifying deep neural networks and taking, I think, which is a really fascinating approach to verifying those neural networks. And we are looking to put together an event with Changliu that's a hands-on event so that you can try some of these activities. So look for that to be announced later this year as well. Give us just a quick moment while we hand over control to Changliu.
Thank you, Steve, for the introduction. And yeah, I'm Changliu. I just joined the Robotics Institute at Carnegie Mellon University. And this work, Algorithms for Verifying Deep Neural Networks, was in collaboration with Tomer Arnon, Chris Clark, and my postdoc advisor, Michael Kochendorfer. So in this work, we are trying to address the problem of how can we verify the properties of deep neural networks so that they can be safe and robust. And the neural networks that we are thinking about are deep feed-forward neural networks, which encode a mapping from an input vector denoted as x to an output vector denoted as y. And we denoted this mapping as f. And there's a structure of this mapping F. That is, it contains several layers. And we call the hidden layer I plus 1 as the hidden layer I minus 1 as zi minus 1. And from the hidden layer I minus 1 to layer I, there's a mapping called Fi. So this Fi mapping is composed of a linear mapping. which is encoded by a matrix Wi and a bias term Bi, as well as a nonlinear activation, which we denote as sigma I. So we denote the value of the hidden node before activation as Z hat, and the value after activation as Z. And both Z hat and Z are inside the hidden layer I. So these are all the notations that we'll use during this talk. So what is the verification problem related to deep neural networks? We actually want to verify input-output relationships. For instance, for certain input variable x belongs to a set curly x, we want to make sure that the output y after the mapping f, so y equal to fx, all the y belongs to an output constraint curly y. So this kind of mathematical problems can encode a lot of real-world problems. For example, it can encode the robustness problem arise from image classification. So for example, here, we have a panda image, and it was correctly predicted or classified as panda. But if we add certain noise, then although from human eye will still classify it as a panda, the neural networks may be confused and predict something else. So if we consider robustness problem, then the mathematical problem for this robustness verification can be posed as, given a certain range of input disturbances, can we still make the same output classification? Okay, so this is the robustness problem. And we can also use this mathematical formulation to encode safety problems. Here we're using an ACAS network scenario. So ACAS network is widely used as guidance for collision avoidance in airplanes. This is we are showing a guidance map for an ego plane to avoid an intruder plane. So if the intruder plane is in the green area, then the ego plane should go to minus 1.5 degrees. If the intruder plane is in the gray area, the ego plane should go by 1.5 degrees positive. But this original guidance is a lookup table, which is very inefficient to store. So people tried to use neural networks to approximate this table, and the approximation result is shown to the right of the figure. So in some of the points, the output of the neural network is different from the original mapping. And you want to make sure that after the approximation, we still can generate correct or safe guidance to the airplane. So why does conventional method fail to verify the input-output constraint of neural networks? This is because the conventional methods are using point-wise verification. For example, if we consider a function f as shown in this curve here, and we want to make sure, given all the x that belongs to this green rectangle, and corresponding y's also lies in this green rectangle, then conventional method just sample a few points along the x-axis and see if the y lies in the green area. If we happily sample all the points that lie in this area, we will arrive at the conclusion that this property is verified. However, it is highly likely that we will miss all the peaks of function f and made a wrong conclusion. So in order to deal with this inefficiency, we actually need to deal with verification problems of continuous sets or continuous constraints. And in order to verify that, we introduce 4 failure modes for the property to be not hold. First is that if we can find a counterexample, then the property may fail. Suppose we have an input space and output space both shown in as the square, and the input constraint as the gray triangle here, and output constraint as this polygon here. Suppose we can find a point in the input constraint that maps out of the output constraint, then we can conclude the verification problem is failed. The second failure mode is that if we can find an adversarial and range of disturbances that can make the output constraint violated, then we can also conclude that the problem is failed. And intuitively, that is corresponding to we map the complement of the output constraint back to the input space. And then we find the minimum disk such that there's no point can belong to the complement of the output. And if this disk does not contain the input constraint, then we can conclude the property is failed. The third result and failure mode is called can be decided through computation of reachability set. The idea of reachability set is given an input set X, we compute the reachable area for all the points inside the set given the mapping F. In this case, the reachable set is the blue area here. If this reachable set blue area does not belong to the output constraint Y, then we conclude the property failed. And recent approaches try to verify the networks and give one of the three results. But most of them actually handle piecewise linear activation functions and explore the linearity of the network to arrive at some efficient algorithms to draw the conclusion. And the majority of those methods only work with ReLU activations. For ReLU, it is just a piecewise function with just two linear pieces. And so in this work, we surveyed the majority of existing methods. And in the survey, we are concerned with their soundness, completeness, and whether they are terminating in finite time. So soundness and completeness means that are the necessary and sufficient conditions for the results of the solvers to be validated. So in other words, if the solvers returns true means the property really holds, then the algorithm is sound. And vice versa, if the property holds, then the solver always returns hold true for those kind of properties without any unknowns, then the algorithm is complete. And a sound and complete algorithm that always terminate in finite time should always give us the correct conclusion of the original property. Okay. So for all the methods that can be used to verify deep neural networks, we classify them, or we find three main methodologies to perform the computation. And the three main methodologies are reachability analysis, optimization, and search-based methods. For reachability-based method, we illustrate its performance on a simplified neural networks with only one hidden layer. So the idea is, given an input constraint denoted by this blue square here, we propagate the geometric objects or geometric sets layer by layer, and in order to arrive at a reachable set at output layer. So in this case, we first propagate it through this linear mapping W1 and B1 and get a tilted set. And then let the set go through the activation. Here we assume the activation is ReLU. So after the ReLU activation, we can only have positive parts of this set. And then we map this set in hidden layer 1 to the next layer, first through the linear mapping, and then through the ReLU activation. And finally, we arrive at this reachable set here. And we can compare whether this reachable set is contained in the output constraint Y or not. If it is contained, then we verify the property hold. If not, we set the property is not hold. So that's the reachability method. And we can also use optimization-based method. In optimization-based method, the problem is usually formulated as a constraint optimization, which minimizes some cost function such that the input belongs to the input set, but the output does not belong to the output set. In this way, the optimization can give us the counterexample of the property. If there's no solution to this optimization problem, then we can verify the property hold. If there's a solution, then the solution can be returned as a counterexample. But in order to solve this optimization, this optimization is very difficult to solve because of the nonlinear and non-convex constraint imposed by the neural network. So in order to efficiently solve this optimization, people develop different methods to approximate the activation functions, because that's where the nonlinearity and non-convexity come from. So current optimization-based methods only considers ReLU activation. And in order to convexify the ReLU activation, which is denoted as this blue curve here, people use triangle relaxation, that is consider relax the affine constraint to a set constraint. Or people can use parallel relaxation to further expand the constraint to a parallelogram. And another method is to introduce another dimension, delta here, which is an integer dimension, and encode the original constraint as a mixed integer problem. The details of these encodings will be explained later. So the last kind of method is called search-based method. There, we can use two kinds of search to search for counterexamples of the problem. So the first kind of search, we can search in the function space because we are considering ReLU activation. So between the mapping from Z hat to Z, there's only two possibilities: whether the activation is, whether the link is activated or not. So that's a 0-1 choice. And then all the 0-1, we can search through all the 0-1 combinations and see if there exists a combination of this 0-1 activations such that an input satisfies the constraint mapped to an output that does not satisfy the output constraint. And this kind of approaches are very similar to satisfiability problem, and some algorithms directly cause set solvers to solve this problem. The second kind of search-based method is called search. Is using search in the input or hidden domain. So the input and hidden domain correspond to only one layer in this network. And they use, sometimes those methods use branch and bound. That is like bisection. So they first search for the whole space and then break it into half, and then further breaking it to smaller and smaller domains and search for counterexamples. And given these three basic methods, we surveyed 17 existing methods according to our classification. So 3 purely reachability-based methods and 4 reachability methods that also use search, and then 6 optimization-based methods. 3 of them only use primal optimization, 3 of them also use dual optimization, and then 4 more optimization-based methods that combines optimization with search. Okay, I'll give an overview of all the methods that we surveyed here. So for reachability-based method, there can be different ways to compute the reachable set different ways to propagate the geometric objects from layer to layer. So the first way to propagate the geometries is through exact reachability computation. So for example, the set before an activation z hat I is denoted by this tilted rectangle. Then we can partition this set into 4 subsets according to their activation pattern. So for the pink part here, both nodes are activated positive. And for the orange part here, none of the nodes will be activated. So we can then propagate each subset through this value activation and finally arrive at the exact reachability set after activation at the I layer. So because the pink set is activated, so the set after activation remain the same. For the orange set, it is projected to 1 point. And for the blue sets, they are projected into lines here. So this method is good in terms of exactness. So there's no over approximation and the method is complete and sound. But the problem is that if we need to keep track of all polytopes, then the number of polytopes would go exponential. The number of polytopes that need to be recorded would go exponentially with the number of nodes in every layer and with the number of layers. So if the neural network goes wider and deeper, it is impossible to keep track of all of them. So then people introduce a second method called split and join. And AR Square, a solver called AR Square used this kind of method. In split and join, we still compute, we still partition the set before activation and compute the new set through this value activation, which is similar to the exact reachability analysis. But before we propagate into next layer, we can do an over approximation of the reachable set at Zi. In this way, we can combine the 4 different sets into one set, and we do not need to keep track of 4 of them. So the number of reachable sets will not grow exponentially as the network goes deeper and deeper. But this is at the expense of over approximation. So the method AI square is sound but not complete. Not complete means they can return false alarm. So the third reachability method is called interval arithmetic. Previous 2 methods use set transformation to compute reachable areas layer by layer. And they keep track of the dependencies among different axes or different nodes. But this dependency is actually expensive to keep track of. So in interval arithmetic, we drop the dependencies among different nodes. And we compute the reachable area for each axis independently. That is equivalent to approximate all the reachable set after the activation as a hyperrectangle, as shown as the dashed line here. But although this computation can relieve some of the computation burden, but it is at the expense of over approximating the reachable set, which make the algorithm even more conservative. So a solver called MaxSense used this kind of method, but in order to minimize the over approximation, they first partition the input space into smaller domains and compute the reachable set for each smaller domains and then combine them together. So another method to minimize the over approximation of interval arithmetic is to introduce symbolic propagation. So I will use two examples to illustrate how symbolic propagation can be least conservative. So the first, so we consider this very simple network with only one hidden layer. And there are two input nodes and only one output node. The input node belongs to 110 and 12. So if we're doing interval arithmetic, we first compute the output bound for this node. Then after using simple arithmetic, that we can get the bound as 3 to 14. And then the next bound as 3 to 22. And then follow, and because these are all positive, so there's no effect after the ReLU activation. And for the last point, we arrive at an interval of -19 to 11. But if we use symbolic propagation, we'll give two symbols to the input nodes x1 and x2. Then the first node in the hidden layer should be x1 plus 2 times x2. And the second node is 2x1 plus x2. And because we can compute the lower bound on these two variables, and the lower bound are all above 0, so there's no effect after ReLU activation. And then for the output layer, we can compute the symbolic representations x2 minus x1, and we substitute the intervals for x1 and x2 to the equation of the output node. Then we arrive at an output bound as -9 to 1, which is much better than the bound computed by interval arithmetic. And a solver called ReLU used this kind of method to compute a tight bound on the output side. So the last reachability method is using network approximation, which calls due networks, which will be discussed in due optimization part. And the FastLen is doing this kind of computation. Okay, so that's all the reachability methods. Then there are three methods using primal optimization. And as discussed earlier, primal optimization mainly tries to find counterexamples which maps X belong to an input constraint to a Y that does not belong to an output constraint. And we need to encode the network function F in order to make sure the problem is trackable and easy to solve. So for existing primal optimization-based methods, they actually use mixed integer encoding. That is, break the ReLU into two parts and encode the choice of different parts in an integer value delta here. If delta equals 0, we only consider the negative part of ReLU activation. If delta equal to 1, then we only consider the positive part of the activation. So if we encode all the activation in this way as a mixed integer programming, then we can break the function into many, many pieces where the number of pieces depend on the number of activations. For example, a network that only contains ReLU activation should be piecewise linear, as shown in F here. Then this mixed integer encoding actually break it into 3 pieces, where each piece corresponds to one linear segment of the function. And then we try to find the optimal value in each piece. And then we can iterate through all the pieces and get global optimal value. There are 3 solvers using this kind of approach: NS-verify, MIP-verify, and IOP. The difference between NS-verify and MIP-verify is that NS-verify use generic encoding that does not rely on the bounds of the does not rely on the bound before activation, where MIP-verify relies on the bound of the nodes. Then iterative LP, IOP stands for iterative LP, only computes the problem in one linear segment. Okay, that's primal optimization-based method. But primal optimization is still complicated to solve due to those constraints. So then we can use dual optimization to make the constraint simpler. The idea of dual optimization is to find a dual network given the objective of the optimization problem. Suppose the objective of the optimization is denoted by this linear objective, which depends on z hat n, that is the output node, and c is a vector and d is a scalar. Then we can rewrite the objective as a linear function of this hidden variable z hat. And the coefficient before z hat is called a dual variable. So we call, and we denote dual variable as nu here. For nu n, it just equal to c, and gamma is a bias. For in this term, for the last layer, it equals minus d. And there can be multiple ways to interpret this dual variable. One way to interpret dual variable is as a co-state or shadow price in dynamic programming. And the second way to interpret the dual variable is as a Lagrangian multiplier. And the third way is to regard this dual variable as a gradient in the backpropagation network, which in this case, the dual variable actually is the gradient from j to z hat. So if we do this kind of encoding backwardly and inductively backward, then we can arrive at an representation of the objective for all the layers. And then we have a bunch of dual variables, and these dual variables form actually a symmetric network as the original network. And the relationship between the dual variables should be derived from the original network. So to derive those variable relationships, we actually need to use the condition that all the objectives should be the same, because they are the same encoding of the final objective. So in order to make sure the objective written in i+1's layer is the same as the ith layer, we need to consider the dual functions of the mapping from z hat to z hat z hat I to z hat i+1, which is the variable in the ith layer, and to the variable in the i+1's layer. So it is easy to compute that the dual function for the linear mapping is just the transpose of the linear matrix W. The thing that is complicated to compute is about this activation function. So the dual of the activation is not properly defined. And in order to provide an upper bound of the estimation of the objective J, we actually require that the dual function times the variable in the original network should be greater than the dual variable times the original activation function. And in this way, when we construct the dual networks, we can map the computation of, so the computation of the objective function that depends on the variable in the last layer can be replaced by the computation of an objective function which only depends on the variable in the first layer, z0 here. And all the complicated mappings in the original neural networks are coupled through this dual variable nu 0 hat. But in order to make this kind of computation realizable, we need to find a proper dual function for the activation, sigma here. And there are different approaches to find the dual function, and they try to minimize the dual function in order to make sure this inequality gap is as small as possible. I will just quickly go through this part. For details, you can refer to our paper that is currently on arXiv. There are 3 methods for DU optimization computation. First is to use Lagrangian relaxation to find this DU function sigma star here. And then we can also use network relaxation. In this way, we can find a linear DU function of the activation. And then the third method uses semi-definite relaxation, and we can also find an analytical solution of the DU function. But this semi-definite relaxation only works for neural networks with only one hidden layer. So that's optimization-based methods. There are 8 more methods. Either combine reachability with search or combine optimization with search. So we will use a series of animations to illustrate how these methods work. For search plus reachability method, there are 5 algorithms. For FastLin, they use binary search of desired input radius, and they compute reachability by network approximation using DU networks. For FastLip, it combines FastLin with the Lipschitz estimation. For ReLU-Val, it search in the input domain through interval split, and they compute reachability by symbolic propagation. For DLV, they perform search layer by layer in all hidden layers. For FastLin, the idea is that we have this input space and an output space, which we try to see how large the disturbance can tolerate in order for the output to still satisfy the output constraint imposed by this gray set. So we can first guess an input range, as shown as this dashed circle here, and then use reachability method to compute a reachable set and check whether the reachable set belongs to the output set or not. In this case, it does not belong to the output set, so we need to shrink the initial estimation. And accordingly, the reachable set is smaller. But this time it is too small, and then we enlarge the estimation of the input radius a little bit, and now the reachable set touches the boundary of the output set, and we are done. So this final radius, final input radius is considered as the adversarial bound for this neural network. And FastLin further introduced Lyapunov estimation to compute the allowable disturbance. For ReLU-Val, the idea is to compute a tight reachable set through compute a tight reachable set by combining search-based method with symbolic propagation. So if we compute a reachable set directly from the original input constraint X here, we may arrive at this dashed square in the output space, which violates the constraint, but the violation may only due to the over-approximation of the reachable set. So in some methods, they minimize the over-approximation by breaking the input set into smaller domains, such as here in this case, they break it into 4 smaller domains and compute a reachable set for all the 4 domains and check if they belong to the output set Y or not. In this case, they belong to the output set, so the original property should hold. But this approach is not very computation efficient, because in the beginning, we are not sure how many subsets should we break into and how large the subset should be. So ReLU-Val use search-based method to break the set iteratively. The idea is, first, ReLU-Val will compute the reachable set using the original set as a whole. And the reachability analysis is through symbolic propagation, as we discussed earlier. But then we find that the reachable set, given the original input set, does not belong to the output set Y. And then we break the input set into two parts. First, we compute the blue area and find that the blue area the reachable set for the blue area belongs to output set Y. Then we compute the yellow area, and the yellow area does not belong to the set Y. So we are done with the blue area. Then we need to further split the yellow area into two more sets. Then we compute the reachable set for these two sets and find that they belong to the output constraint, and then we are done. And the property is verified. So this method is efficient and also minimize the over approximation as much as possible. Then there's a method called DLV, which performs the search layer by layer in all hidden layers. The idea is that in hidden layer I, we'll build a search tree as shown here. So all the dots are the tree nodes during the search. And for every node, we will check if the node maps to the output constraint or not. In this case, we require all the output to be one certain label, that is 1 point in the output space. So for the blue point, it satisfies the output constraint, but for these two red arrows, it does not satisfy the output constraint. Then we map the point back to the input space and see if there's an input that can arrive at the tree node here or not. In this case, the upper node can be arrived and the lower node is not realizable due to over-approximation. Then we will conclude that this upper node is a counterexample which maps an desirable input to an undesirable output. And so this tree structure is also propagated layer by layer together with the propagation of the reachable set. So from layer I to layer I plus 1, we first compute the reachable set as this solid rectangle here. And then we'll try to refine the search tree layer by layer. And actually the search tree can be in high dimensional space that span all the dimensions of the one layer. But that will create an extra complexity to the problem. So the author of the DLV suggests that we can do a low dimensional search, and it can also efficiently find the counterexamples. Okay, that's all the method for search plus reachability, and there are 4 more methods combines search with optimization. For Sherlock, it search in the input domain and use local constraints or global constraints to verify the search. And for BAB, it stands for branch and bound. It search in the input domain and use branch and bound to split into smaller intervals for tighter computation. And for Planet and ReLUplex, they search for feasible activation patterns of the whole network. The idea of Sherlock is illustrated here. Suppose we have an neural network represented by this gray mapping here. We start from input point, showing dot here. We first use local search, which is performed by primal optimization with only linear constraints that only considers the one linear segment of the network, which is the segment that current input is on. So then after this optimization, we'll find local optima of this network. Then we'll do a global search with mixed integer linear encoding, as discussed earlier with NS verify and MM by P verify. And this global search will allow us to jump off the local optima and go to another branch. And then we can do another local search to optimize the point in this local branch. and then we arrive at a better value here. Then another search, global search, and another local search. And finally, it will lead us to the optimal of the network. And then we can use the optimal of the network to verify the satisfiability of the output constraint. For branch and bound, the idea is to compute lower and upper bound simultaneously for certain input segments. So for every input domain, we compute the upper bound by optimization using network relaxation. So the upper bound may not be reliable or realizable. And then we compute the lower bound by sampling. So the lower bound is actually realizable. At the beginning, we compute the lower and upper bound for the whole input space, as shown here. But there's a big disagreement between lower and upper bound. Then we need to split the input space into smaller domains in order to find a tight bound. So first we split into half, and for the left half, we compute the lower and upper bound. For the right half, we also compute the lower and upper bound. But the upper bound of the right half is smaller than the lower bound of the left half, and because we are trying to maximize the objective, so we can drop the right half and further split the left half then. And once the difference between the lower and upper bound is small enough, then we can say we arrived at an optimal solution. So the last two methods are planet and ReLUplex. And these two search in the function space, that is the 0-1 activation patterns of all ReLU activations. Because for each ReLU, there are two possibilities, 0 or 1. We can build a search tree that encodes all the possibilities. And during the search, we can prune the certain branches by optimization-based feasibility check. And actually, Planet uses SAT solvers, and ReLUplex combines simplex algorithms to speed up the computation. And this table is a summary of all the methods that we surveyed, the activation patterns they can allow, and the approaches they are using, and the input and output types they can tolerate, and whether they are complete or not. And all these methods are sound. Not all of them are complete. And for complete method, usually there is a trade-off of scalability. So complete method is usually not very fast for larger networks, but incomplete methods are efficient in handling large networks. And we have introduced a toolbox called neuroverification.jl. It can be downloaded from the GitHub link there. And in this toolbox, we implemented all the previously mentioned methods. Although that is only pedagogical implementation, but we do have very relatively good performance for this method, and it can help verify even larger networks. And we have tested our implementation on a bunch of networks. For example, MNIST networks and ACAS networks. MNIST networks are image classification networks, and ACAS networks are the networks we discussed earlier for generating reference for airplanes. And this table shows the computation time for different methods. And it is in seconds, so we can see a lot of them can be completed. The computation can be completed very efficiently. So, conclusion. We discussed an unified mathematical framework to verify satisfiability of a neural network given certain input and output constraints. And we named three basic verification methods. That's our reachability method, optimization, and search. And through the experiment and through the analysis, we find there's a trade-off between completeness of a verification algorithm and its scalability. And we introduce pedagogical implementations of all these methods in Julia, and it can be downloaded from the GitHub repo listed earlier. For future directions, because in this work, we're considering only feed-forward networks without any loop. So we need to, in order to extend this work to more real-world neural networks, we need to go beyond piecewise linear activations and go beyond feed-forward structures to recurrent structures and address the trade-off between completeness and scalability. And also even go beyond universal approximation theorems in order to analyze the exact function space for a given network topology and better understand those properties. So that's all of my presentation, and our paper algorithms for verifying deep neural networks are currently on archive now. And here's the link to download the paper. And this work is supported by CARS, and I would like to thank Steve for generous support for my postdoc last year. And I would like to thank my postdoc advisor, Professor Kokendorfer, for valuable discussions and suggestions, and also the students, Tomer, Chris, for hard work of implementing all these methods and modifying the code stuff, and also Clark for valuable discussions. And also we receive a lot of comments of the authors of the original papers and original algorithms. And this helped us improve our early draft of our survey a lot. And then we also like to thank the author of lazy sets for their help in our implementation, because a lot of the reachability methods that relies on manipulation of geometric objects is performed by calling lazy sets directly. That's all. Thank you.
Changliu, thank you so much. That was absolutely fascinating. I think in the interest of time, maybe we could have, if there are any very quick questions, please feel free to submit those through the Q&A here on the webinar. Otherwise, if you don't have, if it's a longer, more involved question, I think it might be best to handle it offline in the interest of time. So let me just give it a few seconds here to submit any quick questions. Changliu, maybe just if you could very quickly say, so for those who are interested in downloading the GitHub, downloading your implementations on GitHub to be able to play with some of these approaches individually, what would they need to do in order to be able to do that?
So they need to first have Julia 1.0 and then install Jump, which is the optimization package in Julia, and then install the lazy sets, which is the geometric computation in Julia. Then they can run it freely. Okay, fantastic. All right, Changliu, thank you so much for your time today. Those of you online, if you have questions, feel free to email them to Changliu directly or to me, and appreciate everybody's attention. Changliu, thank you so much for a fabulous presentation. Thank you. All right, bye-bye, everybody.